One of the ideas in our Unit 6 here is about calorimetry. And calorimetry, you can kind of see just by the name, calories has to do with heat or energy, and metry has to do with measurements. So how do we actually go and measure this heat? And the way we do that is we can measure things by heating up some water and see how much the water increases, and that is an indication of how much heat went in. We need to look at two ideas here. One is something called the specific heat capacity, or a lot of times we just call it specific heat, and the symbol for that's going to be C sub P, which is capacity, and that is how much energy it takes to heat up a certain amount of water 1 degree. We want to look at the calculations for this, so we have a formula for this, and we'll be seeing that on our next pages. And we're also going to use our IESA format. So each of these questions will be worth 4 points. One for identifying the variables, write down the equation, substitute in your values, and then calculate the answer. Now, one of the big ideas here is this one called specific heat capacity. And the idea of a calorie, and that's the English unit for heat, is that that's how much energy it takes to heat up 1 gram of water, which is not very much, about 20 drops of water. So heat 1 gram of water by 1 degree Celsius. So maybe go from 4 degrees Celsius to 5 degrees Celsius. Okay, that much energy it would take is 1 calorie. Now, joules is the metric unit, okay, and it's exactly the same idea, only it takes 4.18 joules to heat 1 gram of water 1 degree. So joules are a little bit smaller than calories. Well, obviously about a quarter of the size. This turns into this really handy law, and this law here is, Q equals M delta T C sub P. Now Q, that's the energy, heat energy. It could be heat or just be energy in general. And that's measured in joules right now. The mass, okay, we say the mass of the water, although that could be the mass of anything. So if we're heating water, which is very, very common, then it would be the mass of the water. Okay, and the specific heat capacity is how much energy it takes for 1 gram of water. But we could also be measuring, heating up some metal, heat up some copper, and it would have a different C sub P. You could heat up iron, you could heat up aluminum, you could heat up a lot of different things, and they would have different values of the specific heat capacity, but the same formula. Okay, delta T, delta just means change, and this is change in temperature. So if we had a situation where we were going from 25 degrees and we heated something up to 50 degrees, well then obviously the delta T of that would be 25 degrees, 50 minus 25. If we were cooling down, so say we're going from 30 degrees down to 10 degrees Celsius, then that would be a situation where we have negative 20 degrees for our delta T, because it's always the final minus the initial. So it would be 10 minus 30, and we would get a negative 20 degrees for that. And that shows up once in a while, not usually too confusing. The last one here is the heat capacity, and as we mentioned here before, and heat capacity is 1 calorie per gram degree for if we're working in calories, or 4.18 joules per gram degree. That's a 4 here for water, and that's the number we use quite often. Let's try a couple of problems. So we start off here and say, okay, how much energy is required to heat up 20 grams of water from 30 degrees to 50 degrees, and the heat capacity for water is 4.18 joules per gram degree. Now, by our IESA, first thing we want to do is identify our variables. So we have Q, we have M, we have delta T, and we have C sub P. Now we can see in our problem, we just said that this is 4.18 joules per gram degree. And the delta T, we are going from 30 degrees to 50 degrees. So 50 minus 30, this is 20 degrees Celsius. The mass, okay, we said is 20 grams of water. So this is 20 grams. And Q, they don't tell us that, but it says how much energy, how much energy. So energy is Q, so this is what we're actually looking for. So that's our first one. We've just done our I. We got 1 point. Okay, the equation. The equation is Q equals M delta T C sub P, and we're just going to multiply those three values. We know our mass is 20 grams, Our change in temperature is 20 degrees. And our C sub P, our heat capacity, is 4.18 joules per gram degree. Now, changing colors, we can see that the grams, those are canceling. The degrees, that cancels, and we're left with joules. So the final answer on this is simply going to be 20 times 4.18. For this, I get 1,672 joules. Now, just a quick review here. What have I done? Is I had my I identified my variables. Okay, E, I wrote my equation right up here. S, I substituted in my values right there. And then I finally went back and calculated my answer. And there that is right there. So there's my 4 points. Now, this idea of AISA, some people find that a little tedious, but it is a really good way to build up good skills for solving problems. You know, identify your variables, write your equation, substitute the values, and get your answer. And you find that you will do better overall if you keep this idea of AISA in your head. Okay, let's try a second problem. So I want Q, M, delta T, C sub P. I'll change colors. So what have I got? I've got a 50-gram block of copper, so that's my mass. And notice we're talking about copper. So for copper, we're going to have a different value of C sub P, and what is the specific heat? So we're actually looking for that value this time. So we better have a heat, we better have a delta T somewhere. And we can see what we have here. We have 1046 joules of energy. So that's how much energy went into our copper. I'm going to fill that in. And temperature difference, we're going to go from 10 up to 64.3. So I can do that in my head. 64.3 minus 10 is 54.3 degrees Celsius. So now we've identified our variables. So far, so good. Okay, next let's go back and put in our equation. Q equals M delta T C sub P. And what I want to do is I'm trying to get my C sub P. So I personally like to rearrange my equation to solve for the variable I want. So if I want C sub P, it's going to equal Q divided by mass and delta T. Now that's just the way I like to do my equations. If you would rather, you can just substitute the values into your equation and work from there. So I'm going to substitute now. So Q is 1046, that's a 0, joules. Mass is 50 grams. And my change in temperature is 54.3 degrees Celsius. So I'm going to get an answer, and my units on this, you can see, are joules per gram degrees Celsius, which is what we would expect for a specific heat. The value of this comes out to be 0.385. So that's my final answer, 0.385 joules per gram degree. Now my AISA, okay, you can see here I identified my variables. I wrote my equation. I substituted in my values here, and now I have my answer with the units. So I've got my 4 points out of 4 points. Okay, the last little equation we're going to try here is what is the final temperature when a 90-gram sample of aluminum at 20 degrees absorbs 500 joules of energy, and we are not talking about water, so the C sub P is given for aluminum. So let's go back and write our variables. Q, mass, delta T, and C sub P. And let's start filling in values. Okay, my C sub P is given 0.897 joules per gram degree. What else do I have? I have a 90-gram sample, so that's my mass. And my Q, the amount of energy, is 500 joules. So it sounds like what I can calculate from this is my change in temperature. Now that's not really what I want. I want my final temperature, but if I get the change in temperature and I know I start at 20, then I can figure out my final temperature. Okay, let's change colors here. Q equals M delta T C sub P. And again, I like to rearrange my formula to get delta T, so I'm going to say delta T is equal to Q over M and C sub P. Now you can see what I'm doing. I take delta T, so it equals Q, opposite, and then I need to divide by my mass and my C sub P to get my equation. So this is my equation part. Okay, I'm going to substitute my values in. Change colors again. Q is 500 joules divided by the mass, 90 grams, and my C sub P, which is 0.897 joules per gram degree. Now let's do some units here. By joules, okay, I can see those are going to cancel, and my grams cancel. I've got degrees Celsius on the bottom of my denominator, which puts it up on my top, so my actual answer is going to be in degrees Celsius, which makes sense because I'm looking for my change in temperature. So give me a second, let me calculate. This gives me 6.19 degrees Celsius, but again, that's not my actual answer. My question is, what's the final temperature? And what I figured out is my change in temperature. So if I started at 20 degrees, and I went up 6.19 degrees, then you can see that my final answer is going to be 26.19 degrees Celsius. Now again, we're not terribly concerned about significant figures here, so I would leave that, or I could say 26.2 degrees Celsius. This would be fine. We're doing the right thing. So that's calorimetry. It's a very handy technique for if I'm warming up some water. Warming up water, cooling down water, or warming up any substance and cooling it down, I can determine how much energy is involved. That's it.